Welcome! In this session, we'll explore the problem titled Execution of all suffix instructions staying in a grid. We'll break down the solution step by step, starting with a brute force approach and analyzing its complexities. Let's dive in. In this problem, we are dealing with a grid of size nxn, and we are given a starting position within this grid, represented by start row and start call. The task involves a string of instructions, S, where each character in the string represents a movement direction. Specifically, L means move left, R means move right, U means move up, and D means move down. Starting from the given position, the goal is to determine how many instructions from each suffix of the string can be executed without moving out of bounds. For each suffix S, I, we need to execute the instructions in order and calculate how many of them are valid before hitting the boundary of the grid. The result will be an array where each element corresponds to the number of valid instructions for a particular suffix. Let's consider an example to make this clearer. Imagine we have a grid of size 3x3, and the robot starts at position 0, 1. The instruction string is RRDDLU. For the complete string S, 0, smiley face, equals RRDDLU, the robot tries to execute the first instruction, R, which moves it to the right. However, this movement would take the robot out of the grid's bounds, so it stops immediately. Thus, only one instruction is valid for this suffix. The result for this suffix is 1. Now, for the suffix S, 1, smiley face, equals RDDLU, the robot successfully executes all 5 instructions. It moves down, down, left, and then up without hitting the boundary. Therefore, the result for this suffix is 5. For S, 2, smiley face, equals DDLU, the robot can execute the first 4 instructions before stopping. For S, pet smiley, equals DLU, 3 instructions are valid. With S, 4, smiley face, equals LU, only 1 instruction can be executed, and for S, 5, smiley face, equals U, none of the instructions can be executed as the robot immediately moves out of bounds. This gives the corresponding results of 1, 5, 4, 3, 1, 0. Let's look at another example. Here, the grid is of size 2x2, and the robot starts at position 1, 1, with the instruction string LERD. For the suffix S, 0, smiley face, equals LERD, all 4 instructions can be executed successfully, resulting in 4. For S, 1, smiley face, equals URD, the robot moves up with the first instruction but goes out of bounds, so the result is 1. For S, 2, smiley face, equals RD and S, pet smiley, equals D, the robot cannot execute any instructions without going out of bounds, resulting in 0 for both suffixes. Thus, the output for this example is 4, 1, 0, 0. Finally, consider a grid of size 1x1. Here, the robot starts at position 0, 0, and receives the instruction string RULDR. In this case, since the grid consists of only one cell, the robot cannot move in any direction without going out of bounds. Regardless of the suffix, no instructions can be executed. Hence, the result is 0, 0, 0, 0, 0. The constraints for this problem ensure that the grid size is between 1 and 500, and the string length is also between 1 and 500. Edge cases include scenarios where the grid is very small, the robot starts near the boundary, or the instruction string is long but only a few movements can be executed before hitting the boundary. These constraints and edge cases help define the challenges we need to handle when solving this problem. To solve this problem, let's first consider the brute force approach. The idea here is straightforward. For each suffix of the input string S, we simulate the robot's movement step by step, starting from the given position, start row, start call. As the robot moves according to the instructions in the suffix, we count how many valid moves it can make before it exits the grid. To implement this, we iterate over all possible starting indices I in the string, take the suffix S, I, and simulate the robot's movement from there. For each instruction in the suffix, the robot updates its position based on the direction left, right, up, or down, and we check if the new position is still within the grid boundaries. If the robot moves out of bounds, we stop counting moves for that suffix. While this approach is conceptually simple, its time complexity is O(n squared), because we repeat the simulation for every suffix, which is inefficient for larger grids or longer strings. Additionally, it uses minimal memory, but the repeated simulations result in redundant calculations, making this approach impractical for large inputs. Now, let's move to a more efficient solution, the optimized approach using a single simulation. The key idea here is to avoid simulating the robot's movement repeatedly for each suffix. Instead, we simulate the robot's movements just once, processing the entire string S in a single pass, while simultaneously calculating the results for all suffixes. The insight is that the result for any suffix S, I depends solely on whether the robot remains within the grid while executing the instructions from that point onward. By keeping track of the robot's position after each instruction, we can determine its validity and reuse this information to update results for all relevant suffixes. To implement this, we initialize a results array of size len s to store the number of valid moves for each suffix. Starting from start row, start call, we simulate the robot's movement one instruction at a time. For each step, we check if the new position is within the grid bounds. If the robot exits the grid, we stop updating further suffix results. Otherwise, the current step count is used to update the result for the current suffix and all subsequent ones. This method processes each instruction exactly once, reducing the time complexity to O(n) at the cost of an additional O(n) space for the results array. This optimized approach offers several advantages. First, it is highly efficient because it eliminates the redundant calculations present in the brute force method. By processing the instructions in a single pass, we minimize the computational overhead and achieve a significant reduction in time complexity, from O(n) squared to O(n). Second, it is relatively straightforward to implement, as it involves a single loop and simple boundary checks. Finally, this approach scales well to handle larger grids and longer instruction strings. When deciding between the two strategies, the brute force approach is limited by its inefficiency. The repeated simulations make it impractical for larger inputs. In contrast, the optimized approach is not only faster but also ensures that we calculate results for all suffixes simultaneously, making it the preferred choice. The trade-off here is the additional memory required for the results array O(n), compared to the constant space usage of the brute force method. However, this trade-off is justified by the significant improvement in performance, particularly for larger datasets. The key insight that makes the optimized approach so effective is recognizing that the result for any suffix s, I can be derived directly during a single simulation of the entire string s. This eliminates the need to restart the simulation for each suffix, which is the main source of inefficiency in the brute force method. By leveraging this observation, we achieve a balance between time complexity and space usage, with the optimized approach offering O(n) performance for both. This makes it the best choice for solving the problem, as it is efficient, simple to implement, and highly scalable. Whether we are dealing with large grids or long instruction strings, this approach ensures we can calculate the results quickly and accurately, making it a robust and practical solution for the problem. To solve the problem, we need to simulate the movement of a robot on a grid based on a sequence of instructions provided in the string S. Each character in the string corresponds to a movement direction: U4 up, D4 down, L4 left, and R4 right. The robot starts at a given position, start row, start call, on a grid of size mxn. For each suffix of the string S, the task is to determine how many valid moves the robot can make before it exits the grid. The brute force approach to solve this involves simulating the robot's movement for every possible suffix of the string. The first step in this approach is to iterate through all the suffixes. For each character index I in the string, we isolate the suffix s, I, which represents the sequence of movements starting from that position. Then, for each suffix, we initialize the robot's starting position as row call equals start row start call. This ensures that for every suffix, the robot begins its movement from the correct initial state. After isolating a suffix and setting the starting position, the next step is to simulate the robot's movement based on the instructions in the suffix. For each character in the suffix, we update the robot's position accordingly. If the character is U, we decrease the row value by 1, moving the robot up. If it's D, we increase the row value by 1, moving it down. Similarly, L decreases the call value to move left, and R increases the call value to move right. After each move, we check if the robot's position is still within the boundaries of the grid. A position is valid as long as 0 equals row M and 0 equals call N. If the robot goes out of bounds at any point, we stop further simulation for the suffix. During this process, we maintain a counter to track the number of valid moves the robot makes before exiting the grid. Once the simulation for the current suffix is complete, we store this count in a results list. Once we have simulated the robot's movement for all suffixes, the final step is to return the list of counts, where each count represents the number of valid moves for a specific suffix. This approach ensures that every possible sequence of movements is taken into account, allowing us to compute the desired result for all suffixes. A few important insights can be drawn from this algorithm. First, iterating through all suffixes guarantees that we evaluate the robot's movement for every possible starting point in the instruction string. Second, the grid boundary check is crucial for ensuring that only moves made within the grid are counted. However, this brute force approach has some efficiency concerns, as it involves independently simulating movements for each suffix, leading to redundant calculations. This opens up opportunities for optimization, such as reusing computations from previous suffixes to reduce redundancy. To implement the solution, we use a list to store the results and simple variables to dynamically track the robot's position during the simulation. Analyzing the complexity of this brute force approach, the time complexity is O(n squared), where n is the length of the string s. This is because the outer loop iterates over all indices of the string, and the inner loop simulates movements for each suffix. In terms of space complexity, the algorithm uses O(1) additional space apart from the input and output, as we only use a few variables for tracking positions and results. However, the inefficiency of the brute force method can be addressed through potential optimizations. One optimization involves precomputations. Instead of recomputing movements for each suffix, we can reuse results from previous suffixes by maintaining a cumulative state. Another optimization is to process the string in reverse order. By traversing the string backward, we can apply dynamic programming techniques to optimize the simulation process and significantly reduce redundant calculations. These improvements can help achieve a more efficient solution while still preserving the correctness of the results. The provided solution defines a class solution with a method execute instructions. This method simulates the movements of a robot on an NXN grid based on a sequence of instructions and a starting position. First, a dictionary directions maps movement instructions, L, R, U, D, to their respective changes in row and column indices. For example, L corresponds to moving left, 0 row change, -1 column change. Next, an empty list result is initialized to store the number of valid steps for each suffix of the instruction string. The outer loop iterates through each starting position of the suffix in the instruction string S. For each starting index I, the robot's initial position is reset to start pos, and a counter steps is set to 0. The inner loop processes each instruction from the current suffix, updating the robot's position based on the direction mapping. After each move, the algorithm verifies if the new position is within the grid bounds, 0 equals x less than n and 0 equals y less than n. If the robot remains in bounds, the step counter is increment. If the robot moves out of bounds, the loop is terminated early. After processing all instructions for the current suffix, the total valid steps are appended to the result list. This process is repeated for all suffixes of S. Finally, the method returns the result list containing the count of valid steps for each suffix. The algorithm efficiently handles the grid boundaries and correctly simulates the robot's movements, ensuring accurate results for all suffixes of the instruction string. Here, we begin by defining a class called solution that contains our method execute instructions. This method takes three parameters, n, which represents the size of the grid, start pos, an array representing the starting position on the grid, and s, a string of characters that specifies the movement instructions. We start by creating an integer array result to store the number of valid steps for each suffix of the instruction string. Then, we define two arrays, dx and dy, which act as mappings for directional movements. These arrays correspond to the directions u, d, l, and r, helping us calculate the changes in coordinates for each move. Next, we use a loop to iterate through each character in the string s, treating each index I as the start of a new suffix. For each suffix, we initialize x and y to the given starting position and set steps to 0. This prepares us to process the moves in the current suffix. For each character in the suffix, we determine the direction of movement using the current character move and map it to the corresponding index in the dx and dy arrays. Using these mappings, we calculate the new position by adding the respective values to x and y. We then check if the new position is still within the bounds of the grid. If it is, we increment the steps counter and continue to the next move. However, if the new position goes out of bounds, we break out of the loop since no further moves from this suffix would be valid. Once we finish processing all valid moves for the current suffix, we store the total steps count in the result array at index I. Finally, after iterating through all suffixes, we return the result array, which contains the number of valid steps for each starting index of the instruction string. To solve this problem, let's start by understanding the setup. We have a grid of size 3, defined by n equals 3. The starting position is given as 0, 1, and the instructions we need to process are represented by the string s equals rrddlu. To interpret these instructions, we map each direction to a corresponding change in coordinates. L decreases the column by 1, R increases it by 1, U decreases the row by 1, and D increases the row by 1. We'll initialize an empty list called result to store the number of valid moves for each suffix of the instruction string. Now, beginning with the first suffix at index 0, we process the entire string rrddlu. Starting from position 0, 1, with 0 valid steps, the first instruction, R, moves us to 0, 2, which is valid, so we increment the step count to 1. However, the next instruction, another R, tries to move us to 0, 3, which is outside the grid boundaries, so we stop processing this suffix and append the result, 1, to our list. Next, we process the suffix starting at index 1, which corresponds to the instructions rddlu. Again, we start at 0, 1, with 0 valid steps. The first instruction, R, moves us to 0, 2, which is valid, so the step count becomes 1. The next instruction, D, moves us to 1, 2, which is also valid, bringing the step count to 2. Another D then takes us to 2, 2, which is still within bounds, so the step count increases to 3. The instruction L follows, moving us to 2, 1, and we increment the step count to 4. Finally, we process U, which moves us to 1, 1, resulting in a total of 5 valid steps for this suffix. We append 5 to our result list. Now, for the next suffix, starting at index 2, we process the string ddlu. For the suffix ddlu, we again start at position 0, 1, with 0 valid steps. The first instruction, D, moves us to 1, 1, which is valid, so the step count becomes 1. The next D moves us further down to 2, 1, increasing the step count to 2. After that, L moves us to 2, 0, which is still valid, so the step count rises to 3. Finally, U moves us up to 1, 0, resulting in a total of 4 valid steps for this suffix. We append 4 to our result list. Following this same logic, we repeat the process for the remaining suffixes, calculating the number of valid steps for each one. By the end, we determine that the final result for all suffixes is 1, 5, 4, 3, 1, 0. Let's consider another example with n equals 2, a grid of size 2 by 2. The starting position is 1, 1, and the instruction string is lurd. We initialize the result list as empty and begin processing. For the first suffix, which includes the entire string lurd, we start at position 1, 1, with 0 valid steps. The first instruction, L, moves us to 1, 0, which is valid, so the step count becomes 1. The next instruction, U, moves us to 0, 0, which is also valid, bringing the step count to 2. Then, R moves us to 0, 1, which is valid, so the step count increases to 3. Finally, D moves us back to 1, 1, resulting in a total of 4 valid steps for this suffix. We append 4 to the result list. For the remaining suffixes of the string lurd, we repeat the same process, starting from 1, 1, each time and evaluating the instructions step by step. By carefully tracking the movements and checking if each position stays within the grid, we calculate the number of valid steps for each suffix. After processing all suffixes, we find the final result to be 4, 1, 2, 1, which represents the number of valid steps for each possible starting position within the instruction string. To analyze the time complexity of our solution, let's start by understanding the structure of the function. The outer loop iterates over all indices of the string s, which means it executes m times if m is the length of the string. Inside this outer loop, there's an inner loop that processes the suffix of the string starting from the current index I. For the first index, the inner loop runs m times, for the second index, it runs m1 times, and so on. This forms a decreasing series, m plus, m1, plus, m2, plus 1. The sum of this series is given by the formula, m asterisk, m plus 1, slash 2, which simplifies to O, m squared. Additionally, each iteration of the inner loop involves a constant number of operations, such as looking up the direction, updating the position, and checking boundaries, all of which run in O(1). Combining these observations, the overall time complexity is dominated by the O, m squared, growth of the nested loops. Now that we've established the time complexity, let's turn to the space complexity. The algorithm uses a fixed dictionary called directions to map the movements for L, R, U, and D, which requires O(1) space since the size of the dictionary is constant. The result list, which stores the number of valid steps for each suffix, scales linearly with the length of the string S, so it requires O(m) space. Additionally, variables such as x, y, steps, dx, and dy are scalar values, meaning they consume only O(1) space. Importantly, the input S and the startPos tuple are provided as inputs and are not considered auxiliary space. Therefore, the overall space complexity of the algorithm is O(m), dominated by the storage of the result list. Let's compare this approach to a brute force alternative. A naive solution would involve testing all possible paths starting from each index in the string without breaking early when a move goes out of bounds. While this approach also has a time complexity of O(m squared), due to the nested loops, it incurs additional overhead from redundant computations. In contrast, the optimized solution improves efficiency by breaking out of the inner loop as soon as a move goes out of bounds. This early termination minimizes unnecessary operations, thereby reducing the constant factor within the O(m squared) time complexity. As a result, the optimized approach is computationally faster in practice while maintaining the same asymptotic complexity. Next, let's consider the best, worst, and average case scenarios for this algorithm. In the best case, all moves in the string S are valid and stay within the grid boundaries. Even in this scenario, the algorithm still processes all suffixes of the string, leading to a time complexity of O(m squared). In the worst case, every move starting from the first character goes out of bounds immediately. Here, the inner loop breaks early for each suffix, but since the outer loop still runs m times, the total complexity remains O(m squared). For the average case, the algorithm processes roughly half the remaining characters for each suffix, but the total number of operations still grows quadratically. Therefore, regardless of the scenario, the time complexity is consistently O(m squared). Finally, let's mathematically verify the time complexity. The total number of iterations across all suffixes is given by the sum of the first m natural numbers, m plus, m1, plus, m2, plus 1. This sum simplifies to m asterisk, m plus 1, slash 2, which grows as O(m squared). Since each iteration involves constant time operations like direction lookup, position updates, and boundary checks, the overall time complexity remains O(m squared). To summarize, the algorithm achieves a time complexity of O(m squared) and a space complexity of O(m). It is efficient in calculating valid steps for all suffixes of the string while avoiding redundant computations, making it a well-optimized solution for the problem. One of the most common mistakes in this problem is failing to validate edge cases for grid boundaries. This often happens when the robot starts near the edges, such as at position 0, 0, or the bottom right corner at n1, m1. If you don't handle these cases properly, the robot could attempt to move out of bounds, leading to errors or incorrect results. To address this, always check boundary conditions before executing any moves. Another frequent issue is not accounting for all valid directions. While the standard 4 directions up, down, left, and right are common, there are variations where diagonal or custom direction sets are allowed. To handle this, use a direction array and extend it as needed for additional movements. Additionally, inefficiencies in simulation can be a problem, especially when dealing with long instruction strings. Brute forcing every suffix is computationally expensive. Instead, pre-compute the robot's movement using cumulative sums or prefix arrays to optimize the process. Lastly, some solutions fail to include early exit conditions when the robot leaves the grid. Continuing calculations unnecessarily wastes resources, so be sure to use a break condition as soon as the robot exits the grid. Another important consideration is input constraints. Ignoring constraints like the grid size limit of up to 10,000 in both dimensions can lead to time limit exceeded errors if your solution isn't optimized. Always tailor your approach to accommodate these limits, and use efficient data structures where necessary. When discussing this problem in an interview, emphasize edge cases. For instance, consider scenarios like the robot starting near a boundary, grids with only one row or column, or very long movement strings. It's also helpful to discuss trade-offs between approaches. For example, explain why a prefix sum solution is more efficient than brute force in terms of time complexity. This demonstrates a clear understanding of optimization. Modularizing your solution is another strong point. By breaking your code into reusable helper functions for tasks like boundary checks or movement simulation, you make it easier to debug and maintain. Lastly, during interviews, it's often useful to simulate a small example. Walking through your logic step by step on a simple grid and movement string can clarify your thought process and make your solution more understandable. If you're looking for related problems to practice, there are several that can help reinforce the skills needed for this challenge. For instance, LeetCode 980, Unique Paths 3, involves finding paths in a grid with obstacles, which requires careful handling of movement constraints. Similarly, LeetCode 62, Unique Paths, focuses on counting paths in a grid without obstacles, while LeetCode 63, Unique Paths 2, is a variation that includes obstacles. Each of these problems tests your ability to navigate grids effectively. Additionally, you might explore LeetCode 322, Coin Change. While it's not directly related to grids, it involves dynamic programming and optimal substructure thinking, which are valuable skills for solving grid-based problems. These exercises can help deepen your understanding of pathfinding and optimization techniques, which are often applicable to variations of this problem. When considering alternative approaches, an optimized simulation using prefix sums can significantly improve performance for large grids and long movement strings. By pre-computing cumulative moves for each direction, you can update the robot's position efficiently without redundant calculations. However, this approach does require additional memory for storing the pre-computed sums. Another option is mathematical modeling, where instead of simulating each movement, you calculate the net displacement by counting occurrences of each direction in the string. This method is both fast and memory efficient for straightforward movement scenarios. For variations involving obstacles or constraints, breadth-first or depth-first search can be useful to validate paths. While slower for large grids, these techniques are effective when the problem requires visiting all cells or meeting specific conditions. Finally, dynamic programming is a powerful tool for problems that involve finding optimal paths or minimizing costs. For example, you can use a DP table to track the maximum moves possible from each cell. Each of these approaches has its own trade-offs, so choose the one that best fits the problem constraints and requirements. Great job! We've completed the problem execution of all suffix instructions staying in a grid. Remember key takeaways like systematic simulation and edge case handling. Thanks for watching, and see you next time for more coding challenges. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!